Alright, what's up everyone? Welcome back to Structural Free Learning, and in this video we're going to do stress transformation without Mohr circle, and that means we're going to use stress transformation equations, which I'll write out over here. And hopefully you've seen equations like this and how they were derived. Normally these equations are derived, or at least this set is based on starting out with a plane stress element whose horizontal axis is defined as theta is equal to 0 degrees, or some other axis is defined as theta equals 0 degrees, and then going at a new angle theta rotated counterclockwise. So this would define our x prime and our x axes. The y and the y prime axes would be perpendicular to their respective, prime or no prime states. Then if you take the derivative of these with respect to theta and set them equal to 0, then you can find the principal stress equations and also the maximum in-plane shear stress equations, which look something like this. So here are the stress transformation equations and the principal stress state equations and the maximum in-plane shear stress equations. These equations can be used to solve any stress transformation problem. And so what we're going to do is take this problem over here, which I actually solved once using Mohr circle, and use just the equations to calculate principal stresses and draw the representative volume element, and maximum in-plane shear stresses and draw the representative volume element. So given this stress state here, the first thing we need to do is define a coordinate system, or a local axes for this element. And that means selecting what we consider positive x and positive y. And here I'll just go with the standard plus x to the right and plus y vertical. And by choosing that, we are now able to define our stresses, which tells us that sigma x is positive 20 megapascals, sigma y minus 10 megapascals, and tau xy, because it's on the plus x face in the plus y direction, positive 30 megapascals. And with these stresses defined, now we can go ahead and solve for principal stresses and maximum in-plane shear stress states. And so we'll do the principal stresses first. And the first thing you want to find in this is the angle, or angles really, associated with the principal stress state. And here we're going to apply this tangent 2 theta p. And when we plug and chug, we get this tangent 2 theta p equals 2. Solve for 2 theta p, we get 63.44 degrees. And any positive number is associated with a positive rotation as these equations were defined, which is counterclockwise. So this indicates counterclockwise. And also another thing to remember is that 180 degrees from this, or plus 180, there is another angle that will give you a correct solution, which would be 180 from this is 243.44 degrees, going counterclockwise. Angles actually associated with the principal stress, we got to divide these numbers by 2, is theta p. The two possible answers are 31.72 degrees and 121.72 degrees, both going counterclockwise. So these are the angles associated with my principal stresses. Now I have to determine what the actual principal stresses are, and I can do that using this relationship right here. And here I can just go ahead and plug and chug my values. So my principal stresses are 5 plus or minus 33.54. I have two of them. Sigma 1 I will call my major principal stress, or my most positive, which in this case would be 5 plus 33.54, or 38.54 megapascals. And sigma 2 would be my minor principal stress, would be 5 minus 33.54, or negative 28.54 megapascals. And these are my principal stresses. Here are the angles, and really there's only one last thing to do, and that is figure out which angle goes with which stress. And in order for me to do that, what I'm going to do is go back to this equation here and plug in one of the angles and see what principal stress I get. So if I take this equation, just plug and chug with one of the principal stresses, I'll go with 31.72 degrees. And 2 times 31.72 is 63.44. And when I calculate, I'll get 38.54 MPa, which tells me that this 31.72 degrees is associated with sigma 1. So I can just write here theta p1, 31.72 degrees counterclockwise, and I know the other one, theta P2, or the angle associated with my second principal, or my minor principal stress, is 121.72 degrees counterclockwise. And now I can go ahead and draw the principal stress state. This essentially is my answer for principal stresses and the angles associated with them. And these angles are with respect to the horizontal as I defined it in my coordinate system at the very beginning. And if I wanted to draw that representative volume element, I'm going to start with the line that represents theta equals 0 degrees, which in this case was horizontal. And if I start with sigma 1, I know that's 31.72 degrees from the horizontal going counterclockwise. And if I draw a square with respect to this, so that means the first line I'm going to do is draw a line perpendicular to that this 31.72 degree line. I'm going to complete the square from here. My normal stress on this face is a positive 38.54, indicating that I have a tension or positive arrow going away from the face, and equal and opposite on the other side. And if I look 121.72 degrees from my horizontal, that should take me to this face over here, which would be a line going, I drew this kind of messed up, but it would be this line right here, and this angle would be 121.72 degrees, which would take me to the sigma 2, and that's 28.54 or negative 28.54 megapascals, which indicates compression on this face. And I draw the direction of the arrow and the magnitude of 28.54 megapascals. And this is my principal stress state. So if we go back and look, really, in order to do any transformation towards the principal stress, I only have to plug and chug 3 times. And if you've got kind of a fancy calculator that remembers things, all you have to do is calculate the angles, the 2 angles that are associated with the principal stresses. Then go to this equation right here, plug in 31.72 degrees, get one principal stress, and then plug in 121.72 degrees. And in order to plug in 121.72 degrees, you probably just scroll up in your calculator, replace values, and bam, you would get sigma 2, and then you'd be done. And then you just have to draw the representative volume element out. No need for more circle now that you have a fancy schmancy calculator. What's up?